Okay, so today we're going to talk about potential acoustical gain. What does that mean, you might be thinking? Well, a potential acoustical gain is related to sound systems. And this is a very simple diagram of a very simple sound system. And I want to talk about what the components are of a basic sound reinforcement system. What are they? They're on here. What are the components? What are the parts of this thing? Yeah.
A talker, a microphone, a loudspeaker, and a listener.
There you go. Okay. Some of you are maybe thinking, oh, it's a microphone and a loudspeaker, right? Yeah, and that is true. But we have two other things. We have a listener, and we have a talker. We prefer to use the word talker rather than speaker, right? Because then it gets confusing. So we use talker and loudspeaker. We don't really like to use the word speaker, unless the context allows that to not be confusing. But we use the term loudspeaker and talker or musical instrument or whatever. We try not to use the word speaker to describe that thing because that can be confusing. But that's why. Some people think we're being snooty when we say loudspeaker. And it's like, no, we're not being snooty. We're just being clear. Because the term speaker can mean more than one thing, okay, in the context of our sound system. There's more than one thing in your sound systems that could be described as a speaker. And the reason it's important to consider the talker and the listener in your sound system is that without the talker, there is nothing for the sound system to do, right? Because the sound system is there to make the talker sound louder. And so if there is no talker, there is no point for the sound system to exist. And therefore, the talker is a piece of that puzzle. Likewise, the listener is critically important. Because if there is no listener, then why are we here? Okay, it's that, if the sound system makes sound and no one was there to hear it, did it actually make any sound? I don't know. No one was there to hear it. So the answer is irrelevant. Okay, so we need a listener because we design for those ears. When we're trying to make this work, we're trying to make this work for those listeners' ears that are sitting in that spot. And it matters what they perceive. Okay, so you got to think about all four pieces of this. And this is a very basic system. Obviously, in real systems, you would maybe have multiple microphones, multiple loudspeakers, maybe even multiple talkers, multiple listeners, right? So we're going to keep it simple for now, though. But now I've also labeled some lines, and these represent distances, the very important distance relationships between those components. So the distance between the talker and the microphone has some significance that we'll discuss. The distance, and I'm labeling that ds. The distance between the talker and the listener has some significance, which I'm labeling d0. The distance between the microphone and the loudspeaker has some significance, and I've labeled that d1. And the distance between the loudspeaker and the listener is also significant, and we will call that d2. Does that make sense? It's just a label that we can use in a mathematical equation in a moment. Okay, so great. Most of you have probably done this before. Set up a microphone, plugged it in to a amplifier / loudspeaker, maybe through a mixer, and you've had someone talk into that microphone, and you have tried to make it louder. Now, we've learned how we can figure out how much sound should be able to come out of that loudspeaker, right? That's what we've been focusing on so far, is how much sound could we make come out of that? How loud is it possible for it to be? And the answer is pretty loud, right? Once you kind of factor in the power amplifier and the sensitivity of the loudspeaker and the distances in the air and everything, it's possible to make quite a lot of sound. And yet, we hardly ever get there. We hardly ever reach that theoretical potential. We know that that loudspeaker system is capable of delivering 100 dB SPL to the listener. We know it's capable of doing that, but we hardly ever hear that happen. And why might that be? What are the limiting factors there in getting you to get to that point, given a scenario like this? What stops you from getting there? Ah, yeah. Usually you get feedback long before you ever get to that 100 decibels, right? I mean, you're cranking things up and you're turning it up and you get to a point where it's like, yeah, that it gets so loud that it starts feeding back. And feedback is when the sound system gets that ring in it, that sine wave that just kind of gets out of control and gets louder and louder and louder the longer you let it go. And everyone covers their ears and looks at you with, nasty looks and makes you think you're an idiot. And like that's it. Like you don't get to make it any louder than that because the sound system just isn't allowing you to do that. I mean, it's possible for it to get louder, but the only thing that gets it getting louder is that sine wave. And the sound you care about is just staying the same. And that's, that's a problem. So that's what we're talking about today, is when we say potential acoustical gain, what we're talking about is how much louder can we make it before we hit feedback? And that's different from the theoretical potential of the sound system to be loud, right? So let's talk about how this happens. How does feedback happen? Well, feedback happens because some of the sound from the loudspeaker comes out and finds its way back into the microphone. Okay? So the microphone doesn't just pick up the talker. The microphone picks up anything, everything. Everything around it, it picks up, okay? Including the sound coming out of the loudspeaker that is the louder version of the talker. Some of that makes it into the microphone. And we can tolerate a certain amount of that. But eventually, we get to a point where the sound coming out of the loudspeaker arrives at the microphone at the same loudness as the sound from the talker. So when those two sounds hit the microphone at the same level of loudness, that's when feedback begins. As long as the natural sound from the talker is hitting the microphone louder than the sound that's coming out of the loudspeaker, then it won't feedback. But when those things become equal, that's when feedback begins. Now, of course, if the sound from the loudspeaker is hitting the microphone louder than the sound from the talker, then it definitely feeds back. But it starts to happen when those two sounds are equal. And we call that unity gain. So the gain around this electroacoustic system is unity, meaning it's the same. The sound comes out of the loudspeaker, hits the mic at the same level as the sound from the talker. Unity gain means no gain. We're not doing anything. We're not making any difference, at least at that spot where the microphone is. Okay. So what's going on here is that trip that the sound coming out of the loudspeaker makes through the air will take a certain amount of time, right? Because we know that. We know that sound takes time to travel through air. So there is a difference of time that in this diagram I'm calling delta time. And you have the initial sound from the talker hits the microphone here. And then some amount of time later, that initial sound comes out of the loudspeaker, goes through the air, and arrives at the microphone. And that amount of time is going to represent some multiple of a full wavelength for a certain frequency. Because we know that frequencies have wavelengths, and wavelengths can be measured in distances. And there is a very clear relationship between distance and time with sound. Okay? We know how fast sound travels, and therefore we know how much distance it can travel in a given amount of time. So given this delta time, there is a distance involved there. And that distance will certainly be some multiple of a wavelength for some frequency that is hitting that microphone. So whatever frequency has that wavelength, that frequency will be perfectly in phase with the version of it that's coming off of the talker. So those two sounds will be perfectly in phase, and therefore they will combine together at that microphone at the same phase and the same level, and therefore what happens to them? What happens when two identical sounds combine at the same time at the same level? They get louder, or yes, the bigger word would be constructive interference. But they get louder, right? Now that time that one of them gets louder, others will get quieter, right? And that's cone filtering. That's what Kat was getting at. So yes, cone filtering happens, but there will be some frequency that will suddenly lock into phase and get louder. And it's whatever one is the loudest, right? Whichever sound has some multiple of wavelength relative to that amount of time that is also the loudest will be the one that hits the microphone at the same loudness as the talker, and that's the first sound that feeds back. Yes?
So when we hear feedback, we hear a sine wave, and that's because that loudest frequency is what causes it to feed back, and
Yeah.
then it kind of builds on itself.
Yeah.
But what about like the what are they called? Like the overtones of that frequency. Like if you doubled it,
Yeah.
if you tripled it, that kind of thing. Like, did those also ring out?
They can, but they usually don't, because the fundamental is the one that runs away first.
Gotcha.
Okay? And so because the fundamental runs away first, those harmonics don't behave the same way because they're not getting caught as quickly. And generally speaking, when you have overtones, those are not the same level as the fundamental in any complex tone, right? So like my voice, there's a fundamental frequency to my voice, and my voice has harmonic frequencies, but the harmonic overtones are not the same loudness, right? So it's the fundamental that usually hits first.
So what would happen then if instead of having a complex waveform, you played white noise into the microphone to generate that feedback? Would there be multiple? Because white noise is all
Yeah.
frequencies equally loud, right?
It could.
So,
You could get multiples to happen at the same time.
Okay.
I mean, that's not a typical scenario because we don't really ever do that, but
I think that would be a cool experiment.
well, the closest thing to that I could say is this, and you may have experienced this sometimes. Maybe you've been running things and it's fine when, like, if you're doing a live band or something, the band is playing, everything's fine, sounds great. They suddenly stop playing and then suddenly feeds back, and you didn't touch anything. Why? Well, because the system was, that complex tone that was going through the system was this mix of all the sounds they were making, and that's what was kind of like locking in on these phase relationships. They stopped playing, and what's left is the room tone, right? What's left is the room tone, the white noise of the room, and now that's the thing that's getting amplified, and that's why stuff starts feeding back. So if you don't do anything and you don't like cut those mics out, then now that's basically what's happening, is you are just amplifying white noise. And yes, that absolutely will catch on and lock into those phase relationships much faster than the complex tone that is louder that the band is playing, right? So that's what's happening there. The answer to that question is mix better, right? So when they stop playing, get rid of the mics, right? Don't leave them on, okay? So yes, this happens. Some frequency locks into that 0-degree phase relationship, gets a 6 dB boost, and then goes back around that path again, gets another boost, gets another boost, gets another boost. Every time it boom, 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 keeps going, and it just gets louder and louder and louder the longer you allow it to continue. Okay? And usually that doesn't happen because you figure out what's going on and you stop it by muting a channel or cutting a fader or something like that, right? But now you know that there's a there's a limit, right, to what you can achieve, and that's really frustrating. But I want you to understand, and the way to understand how to fix this problem, you have to understand why it's happening in the first place. And the reason it's happening is because the sound from the loudspeaker is hitting the microphone at the same level as the sound from the talker. Okay, and when that happens, that's when feedback begins. So let's take a look at what that result can be. So if I'm going to just put some distances here into this diagram. So I'm going to say that ds, the distance between the talker and the microphone, is 1 meter. The distance between the talker and the listener is 7 meters. The distance between the microphone and the loudspeaker is 4 meters, and the distance between the loudspeaker and the listener is 6 meters. Now, and let's assume that the talker is producing 70 dB SPL at 1 meter, and that's the distance to the microphone. So it is the talker's voice is hitting the microphone at 70 dB SPL. Okay? Well, in that scenario, we know that feedback will begin when the sound from the loudspeaker hits the microphone, also at 70 dB SPL. Right? So acoustical gain, in other words, the gain that we are able to make, the difference we are able to make, acoustical gain is defined as the difference in loudness as perceived by the listener between when the sound system is turned off and when the sound system is turned on. So if we decide not to show up to work, and that talker stands up on that stage and starts talking, and we didn't show up to turn on the sound system, the listener will hear something. Right? That person's voice will be on that stage, and they will say whatever they're saying, and some amount of that will make it to the listener's ears naturally. If it's a relatively small room, they'll probably hear a lot of it, right? If it's a big room, they might not hear very much of it at all. If it's a big stadium, for example, yeah, they're not going to hear much of that. There's just too much distance involved. But the listener will hear something. Now, and that will be whatever it is. Then we decide to show up for work, we turn on the sound system, we do our job, and hopefully it's louder. Okay, that's our job, is to make it louder. So hopefully it's louder, and the amount by which it is louder is called the acoustical gain. It's our gain. What did we gain by being a good sound designer? We gained 10 dB, or 20 dB, or 15 dB. We made the show 20 dB louder. Right? That's what acoustical gain is. You got a question, Eric?
Oh, yeah, I was just going to say if there was such thing as acoustical loss, but that's kind of pointless because you're turning on the sound.
Yeah, you can't really lose. Okay. Let's see here. I think I've got. No, I don't. Okay. So let's figure some of this out. How loud is it at the listener without the sound system? Right? Let's pretend the sound system isn't turned on. What will the listener hear? Well, if the talker is producing 70 dB at 1 meter away, and the listener is 7 meters away, then we could figure that out by doing 70 dB minus 20 times the log of d0 divided by ds. Right? That equation, using those two distances, will give us a dB difference. Okay? So I can do 20 times the log of 7 divided by 1. And anybody want to run that? What is that? What is 20 times the log of 7 divided by 1? Say what? 16.9. Did anyone else get that? Yep. 16.9?
Yep.
Okay. So what is 70 minus 16.9?
53.1.
Yeah, 53.1. That's what's left, so dB SPL. So that's how loud it is just without us turning on the sound system. So the listener will hear 53 dB SPL natural sound at the listener, right? So great. That's not a whole lot of sound. I mean, 70 dB SPL, that's fine. That's about how loud I'm talking right now. So the talker's doing a reasonably okay job. But what's left after traveling 7 meters is only 53. That's not a lot, actually. That's pretty quiet. So they're probably going to want to hire a sound person for this to make that louder. OK, so they hire a sound system, or a sound person to make a sound system. Now, feedback will happen when the loudspeaker hits the microphone at 70 dB SPL. So if that's happening, if the loudspeaker is hitting the microphone at 70 dB SPL, how loud will the loudspeaker be at the listener? If it's 70 here, how many is it at the listener? Well, we could figure that out by saying 70 minus 20 times the log of the distance from the loudspeaker to the listener divided by the distance of the loudspeaker to the microphone. Those are two distances, right? And there will be a different amount of sound that will arrive at the other end for those two distances, right? It'll be louder, in this case, because D1 is shorter, we know it will be louder at the microphone than it will be at the listener, right? So it's going to be less than 70. We know that because it has to travel farther. So what would that be? What is 20 times the log of D2 divided by D1, or 20 times the log of 6 divided by 4? Anyone else get that? One more? One more person get 3.52? It's not right till 3 people get it. It is? OK, excellent. It's possible for 2 people to make the same mistake. It's less possible for 3 people to make the exact same mistake. So, OK, 3.52 is that. So that what would be 70 minus 3.52? $66 point what? 48. Yeah, I'm calling that 66.5. I'm just rounding that. OK, so we turn the sound system on, and we can make up to 66.5 dB SPL worth of sound before it feeds back. Like that's when it feeds back, is when we achieve 66.5 dB SPL. OK, so what is our gain? Well, our gain is that 66.5 that we can make with the sound system subtracted by the amount of sound that the talker was doing all by themselves. And that difference is 13.5 dB. So our gain is 13.5 dB. That's our acoustical gain. Yes, Jesse.
So the potential acoustical gain is the maximum amount of gain that you can get from your current sound system.
Yep. Yep, before it feeds back.
Before it feeds back.
Or rather, when it feeds back. It feeds back when you achieve 13.5 dB.
What
Okay.
is your general rule of thumb regarding the headroom that you leave prior to feedback?
Yeah, so there's a couple of things we need to think about, because 13.5 is when it feeds back. So we're actually never going to really technically achieve that, because that is when it starts feeding back. So we want to be below that point. My rule of thumb is I want to be 6 dB below the point at which it feeds back, for sure. Because in that last 6 dB, that's when it's like starting to and you've maybe heard that happen. It's like it's not technically locking in one sine wave and that gets out of it, but you can hear it kind of getting a little ringy. And that happens in that last 6 dB before you hit that unity gain point. So I want to be 6 dB below that. That's usually my rule of thumb for how much room I want to give myself between where I'm going to be operating and when I know the feedback happens. Yeah?
And is that 6 dB below at dB below the crest factor?
Well,
Because we just learned about the crest factor, so I'm
yeah. So the crest factor is really about the signal, okay? And every signal has a different crest factor. But your sound system is going to have a certain amount of headroom, and what that's about is here is how much sound RMS, whatever loudness I'm trying to achieve. I'm trying to achieve 90 dB SPL at the listener. I need to design a sound system that is capable of delivering 10 dB more than that, or whatever, because that's my crest factor and I don't want to clip, right? So I want to be able to hear that and still not clip the peaks, okay? So you're going to design the sound system that can do that. What we're talking about right now is you may not ever get to there if your acoustical gain before feedback is less than that amount. And whether that's RMS or peak at this phase of the conversation is not really relevant.
Both of them are a limit. Whatever
Yeah.
is lower. Like
Yeah.
If you feedback, then you feedback, and you have to bring it down.
Right.
But if you clip, then it's going to sound like shit, so you have to
Right.
bring it back down
Yeah.
anyway. So,
Yeah.
Okay, so I guess it doesn't really matter.
It doesn't really matter yet. I mean, eventually you might have to think about that, right?
Yeah.
But right now we're not thinking about that.
All right.
Okay, so great. We can make 13.5 dB of a difference. That's actually not very good. If you don't have at least 20 dB of potential acoustical gain, you're not really doing much to earn your paycheck. Okay, 13.5 is not very good. So that's not good. So we'd like to make this more than that. But here's something I want to just make sure you can wrap your head around for just a moment. So I have written where it says combined equation. That is the math we just did all strung together. Okay? 70 minus 20 times the log of d2 divided by d1 minus 70 minus 20 times the log of d0 divided by ds. Right? That's the math we just did, strung all together into one long equation. Okay? Now, below it is another equation that I'm calling simplified. And it's just simplified in that it's a few less variables or a few less bits of information. Someone run that equation. 20 times the log of d1 divided by ds times d0 divided by d2. That's not what I got.
Oh, that was my total. When I minus the 6?
Oh, yeah, when you minus the 6.
Oh, sorry.
Don't worry about minusing the 6 yet. So here's how I break it down. I do 4 divided by 1 and 7 divided by 6. And that's 4 times 1.67. And that's 4.67. And then I do 20 times the log of 4.67. Well, the log based on the logarithm of 4.67 is 0.67. So 20 times the log of 0.67 is 13.38. Okay, that's what you got? Okay, we get the same answer, right? I mean, we had 13.5 before, as compared to 13.38, and that's dB, and we know that like a 0.1 of a dB is nothing, right? That's nothing. In real life, that's nothing. So those are the same answers. So we've proven that this other equation works, okay? But what is different about that second equation?
The simplified second equation?
Yeah, what is different about it?
Well, I mean, the 70s are gone. But
The 70s are gone. And what do the 70s mean? What do those 70s represent? How loud the talker was. What does that tell us about gain before feedback? The level, it is independent of the level of the talker. The loudness of the talker has nothing to do with it. Okay? Because we can eliminate that variable and get the same answer. And therefore, that variable doesn't matter. So what does that mean? That means, gain before feedback is independent of the level of the talker. It does not matter how loud they talk. Your gain is the same. We just proved it. Now, how many times have you blamed those poor actors on your feedback problems?
It's very easy to blame actors.
Right. But that blame is misdirected, right? The fact that your sound system is feeding back is not their fault. It has nothing to do with how loud they are talking. Okay? And we just proved it with math. Now, what is true is that in small rooms where their voice does not have to travel very far before it hits the listener, in small rooms, if they talk louder, then the listener hears something louder, right? So that is true. The listener will hear something louder if the actor talks louder. And in a small room, that might mean that you need less gain in order to achieve intelligibility, right? The amount of difference that is required of you to make to get the level you want might be less in a small room if the actor talks louder, just because, the listener is hearing more already, and therefore the amount of difference you have to make might be less. But that doesn't mean that your sound system has more gain. Your sound system's gain has not changed. The only thing that has changed in that scenario is that you need less gain. But your sound system will still feed back at the same time in the same way. Okay? If our sound system has 13.5 dB of gain, that just means that whatever that actor does, we can make it 13.5 dB louder than that. That's all that means. We can make a 13.5 dB difference from whatever they do. Whether they do something quiet or loud, 13.5 dB is all we can do. In a big room where that sound has to travel hundreds of feet, it really doesn't matter how loud they talk. None of that natural sound is getting to the listener ear that's any useful anyway, right? So whether they talk loud or quiet doesn't really matter for your gain before feedback, right? Because it's not impacting what the listener hears. But your gain is fixed. It's a fixed thing unless you change something, right? But changing the actor, making the actor do something louder, does not change your gain. Your gain stays the same. So stop blaming the actors on your feedback problems, because they can't fix it, okay? You can make them talk louder all you want, and it's not going to change your feedback problem, okay? And so you get to make them feel bad, and you don't actually fix the problem. And so all you've accomplished is make them feel bad. And actors that feel bad and self-conscious don't act as well. Did you know that? Yeah, I mean, actors that are walk out on that stage feeling like they are screwing something up, they don't do a very good job acting when that kind of stuff is in their mind. So you are not helping anyone by planting that seed in their mind that they are ruining the show because they are not talking loud enough. All you're doing is making everything worse. You are not solving your problem, and you are making them do a worse job at their job, and nothing got better. Okay, so stop blaming them.
It's their fault. It's still their fault. Even if it's not their fault, it's their fault.
So let's talk about what is really going on here. So, and how we might actually fix it. So this is a little animation that we did, that Eric did for our book. So some of this is stuff we've already talked about. So there's another piece of the sound system that I just want to make sure we remember, and that is the person operating the console. They are part of this equation in that we cannot achieve that 13.5 dB of gain if they don't push the fader up, right? So they are a part of this problem. So if gain before feedback is not about how loud they're talking, then it is about something else. And it's actually about geometry. It's a geometry problem. It's not an actor problem. It's a geometry problem. It's about distance. It's about the relationship of the distances between the parts of your sound system. And if you get those distances wrong, then you're not going to have very much gain. So, here is the equation, right? And I've tagged some distances on this thing. Now, in this situation with these distances, I would have 10 dB of acoustical gain. Okay? But we can move these things around and see what changes. So what if I move the loudspeaker around? Okay, it changes the result. So if I bring the loudspeaker back here, gain goes down, right? If I put it here, now I only have like 3 dB of gain if the loudspeaker's there. If the loudspeaker's there, put it up higher in the air, it's 7 dB of gain. Back where it was, it's around there. What if I bring it all the way over here and put it right over their head? Okay, I have 31, almost 32 dB of gain. That's pretty good, right? We could do that.
I think that's the perfect place.
That'd be awesome, right? If we could put a loudspeaker like in front of, right in front of everyone, one for every seat.
Just chill down.
That'd be awesome. Like, what could we do with that? That'd be so.
It is worth it if it's worth getting sued for it.
Why would we get sued?
Because people are going to be complaining about the loud volume.
Well, it wouldn't have to be loud. That's what I'm saying. Like, it's right next to them. It doesn't have to. We're not eating up as much sound by traveling through the air, so it doesn't have to be very loud. Okay. So there's a solution. We've broken that 20 dB threshold I was telling you about. Great, perfect. Okay. Well, maybe that's not practical, so we're going to end up maybe something like this. Well, we could maybe move the listener around. Interesting enough, if you get them closer, the gain goes down. Why? Because the natural sound from the talker gets louder, right? And so the difference is less. Okay.
Well,
So-
also, is this taking into account like the loudspeaker is pointing more towards the?
No, we're assuming omnidirectional right now.
Oh, okay. I got you.
We're assuming omnidirectional loudspeaker, omnidirectional microphone. We're not. Don't worry about directivity yet. We'll get there. All we're worrying about is distance right now. Well, here's we can move the microphone. Okay, and in this scenario we would have no gain before feedback. This is the choir microphone scenario, or the floor mic scenario. Right. So maybe you're floor mic. Maybe you're doing floor mics. Okay, and the loudspeaker is like right above the edge of the stage, and that's where you got the mic, and the actor is like really far away. You got 2 dB of gain. That's nothing. You may as well not show it for work. Okay, you've maybe had this situation. Okay, where somebody says, "I know, put out floor mics," and you're like, "I can't get anything out of these before they feed back." This is that scenario. Okay. So we can, but what if we get this? What if we do this? What if we move the microphone and get them really close? Oh, look at that. We can get 40, almost 39, almost 40 dB of gain. Let's see if I can get it up to 40 if I just tweak, right? So if I move things around, I can make this better, okay? So what do we learn? There are some relationships that I want to make sure that maybe you picked up on. So the first relationship is that moving the loudspeaker farther away from the microphone will increase your gain. Okay? Why? Because the farther away the loudspeaker is from the microphone, the more air there is between those two things, and air soaks up sound. So it will be quieter at the microphone, the more air it has to go through to get there. Okay? So moving the loudspeaker farther away from the microphone will increase your gain. Loudspeakers right next to microphones is rarely a very good idea. Okay? The next relationship is if you can move the loudspeaker closer to the listener, gain goes up. Why? Because now you've created less air for that sound to go through before it hits the listener. Therefore, it hits the listener louder. And if you can do that while also getting it farther away from the microphone, then it's a double whammy, right? Because getting it farther away from the microphone, it goes up. But if you can do that and get it closer to the listener at the same time, you get to add that twice. Okay? And the last one is get the talker close to the microphone. The closer you can get to the microphone, the more gain you get. Okay? So if you're going to blame the actors about something, just blame them for their mic technique. Like if they're holding the microphone all the way out here or down at their belly button or something, that's something you can give them a hard time about. Or rather, you don't give them the hard time about it. Have the director give them the hard time about it. I try not to talk to actors as much as I can. Not because I don't like them. They're usually very lovely people and very nice and fun to talk to. But I find that, if I start talking to them about things, I say it the wrong way and it kind of gets in their head and then they start not acting very good because I say it the wrong way. So directors spend a lot of time learning how to talk to actors. And so I usually go to the director and I'll say, hey, can you just go talk to them, get them to hold that microphone closer? I think I can make, this would be better if they would get it closer. So let the director go have that conversation with them, and they'll know how to say it in a way that will get them to do the thing that you need them to do without, messing up something else. But if you can do that, that makes a pretty good difference, okay? So those are some strategies, okay? If you're having gain before feedback problems, get the loudspeaker farther away from the microphone. Get the loudspeaker closer to the listener. Maybe both at the same time if you can pull that off. Get the microphone closer to the talker. The closer you can get it to the talker, the better. This is, by the way, this is the reason why we stick microphones on actors' heads. Because we want to get it as close to the actor as we possibly can. Like the best place for me for a wireless mic is right here in front of their mouth. So inside their mouth would be even better if I could get it, right? Like close as possible. I've only ever gotten that once with the thing right here in front of them. I only got that one time. It was glorious. It was wonderful. I had all the gain in the world, more than I ever needed. Okay, but you never ever get that. The Pretty Committee usually shuts that down. But so you want to get it as close to this spot as you possibly can, and so somewhere on their head is usually pretty good. So this is 6 inches here, and that's like somewhere on their head, like around their hairline. That's usually within 6 inches. That's pretty good. Okay, that's why we do that. So okay, a couple other things. Let's introduce directivity to this equation. So microphones can be directional in the same way that loudspeakers can be directional. Microphones are just backwards loudspeakers. Did you know that? They're just backwards loudspeakers. They're the same thing. So they behave really the same way, just backwards. So let's take a look at how this would work. Now, if we leverage directivity to our advantage, we could get it so that the loudspeaker will be hitting the microphone at an angle where the microphone is less sensitive, and therefore there would be some extra dB of gain we could add into the equation here as a result of that. So here's a situation where I've got 4.5 dB. This is not the geometry here is not very good. The relationships are not good here. But if I switch to a cardioid microphone, I can get 12 dB more of gain. If I switch to a supercardioid, I can get 30 dB of gain. Why? Because I've positioned that node, the place where in a supercardioid, the place that it is the least sensitive is at that angle. And therefore, it's really not picking up the sound very much there. So I'm getting an extra 22 dB of gain by getting the microphone the right directivity and positioned in the right spot relative to the loudspeaker. Now, if I do a cardioid, the cardioid is least sensitive right in the back. So I would want to do this. All right? I'd want to try to get the loudspeaker positioned as close as possible to that cancellation point right in the back of the microphone. And here I'm getting, there I get the 20 dB of gain, right? As opposed to 12 there, but I can get 20 there. Now in this case, I'm also getting it farther away from the microphone, which helps as well, right? But if I could somehow move, this is as far down as I can move it in the animation, but if I could get it down right behind the mic, then I'd get pretty good gain, okay? So there's a reason why we have microphones that have different kinds of directivity. In fact, some microphones have a little switch on them that lets you change their directivity. And this is why you would want to change it. Because maybe the place where you need to put the microphone, like there's not a lot of options just because of all the things that are around it. You're cramming it into an orchestra pit, and you don't get a whole lot of flexibility on where you put it. And so wherever you have to put it, you look at where's the nearest loudspeaker that is going to have the sound of this mic coming out of it. And maybe that's like a monitor wedge that's like sitting right next to that that musician. And if that's the case, you look at where the monitor wedge is, and you figure out, okay, based on the microphone pointing here and the wedge being there, which polar pattern is going to get me the least amount of sensitivity from the direction of that monitor. And if the wedge is coming directly to the side, a figure 8 pattern would be the best, right? Because it's the least sensitive from the side. If the monitor is right behind the mic, okay, well, cardioid would be best for that. If the monitor is over here, so like let's say you've got a singer, and they've got a mic here, right, on the stand, and they want a monitor wedge right for them. Well, if you could do this, if it's this, I would want to put the wedge right in front of them here, and I would want to drop the mic down in height just enough so they would have to tip it up in order to have it pointed at them. And now that node on that cardioid mic is pointing straight at the wedge, which means the least amount of sensitivity. So I'd get the best gain there. Well, maybe they don't want it right in front of them for some reason, or you don't want it right in front of them, or the pretty committee doesn't want it right in front of them, or something. It doesn't really matter, but maybe that's not an option because there's a light there or something. I don't know. And so in that case, you would have to move it to the side. Okay, well, if it's over here to the side, then you would want to do a supercardioid, right? Because the supercardioid actually picks something up right there, but it doesn't pick up very well over here. So you swap it out for a supercardioid mic. That's the difference between like an SM58 and a Beta 58 is cardioid versus supercardioid. So you're doing the SM58 if it's there, and then you got to move the wedge over here. So it's like, oh, well, let me swap out for the Beta 58, and now the node's there. And maybe then the performer's like, well, but then it sounds like it's coming from one side, and that's freaking me out because I don't hear it. Great, you can put two, one over here and one over here, and there's a node over here on this side too. So both wedges are hitting the mic at the cancellation point for the microphone directivity. Okay, so picking the right directivity and the right position of the loudspeaker relative to that is how you get your gain. Okay, hopefully the loudspeakers are nowhere near the mics, but sometimes that can't be avoided. Okay, any questions about that? That make sense? Okay. What about the loudspeaker? Well, loudspeakers can be directional too. We know that. And that can have an impact on how loud things are. So in this scenario, where I've got the supercardioid mic, which lines it pretty darn close up to the node, I get 25 dB of gain just as a result of that directivity. But then I've got a loudspeaker that is pretty directional on the vertical axis. It's 40 degrees between 6 dB down points. And then, minus 12 degrees is wider, but, the amount of sound left over to hit the microphone is less, and therefore I get another 25 dB as a result of that. So I'm doing pretty good now. So let's take a look here. Like if I go 90 degrees, I'm at 52.3 dB, 40 degrees, 58.3. And so, if maybe I have to do the 90 degrees, all right? So in that scenario, I would want to just get it far away and at the node as much as I can. I'm still at 55 dB of gain. That's pretty good. An omnidirectional mic, which is what we usually do for theater, for like musicals, we use omnidirectional microphones. Why? Because we can never get it pointed right at their mouth. Okay? And the microphone sounds different when it's off axis if it's directional. But if it's omnidirectional, it sounds the same no matter which direction you point it. And so no matter where we put it on their head, we're not worrying about the frequency response because of directivity. So we use omnidirectional mics because the pretty committee doesn't allow us to control keeping the mic on axis. Okay? So if you can get that, if you can get the mic right in front of their mouth, like I did that one time, then by all means, go with a directional capsule, right? Because there's no reason you need to be worrying about picking up sound behind the mic, right? Because it's right there in front of their mouth. But generally speaking, if you can't get this, then you're going to have to go with an omnidirectional, just because, you can't ever get it pointed straight at their mouth, okay? So in an omnidirectional situation, all you really can work with is loudspeaker directivity and positioning. And if I did this, I only got like 25 dB of gain, so I would really want to be, if I'm looking for that 50 again, this is my only option. I've got to get the loudspeaker closer to the listener. Or I could get the microphone really darn close to the actor, which is what I do with those lav mics. And now I'm good. I'm fine. I can leave the loudspeaker where it was. I can even go back to the 90 degrees. I've still got 64 dB of gain. Okay? That make sense? All right. So you can utilize your first line of attack when you're trying to get your gain for feedback to go up is to move things around. And you've seen now that there is math you can do to predict this problem. You shouldn't be surprised when you walk into the space and start using the sound system and find out you don't have any gain before feedback. You should not be surprised by that. You can do the math ahead of time and you'll know what kind of problem you have. So if you can find that out before you go in there, then you can move things around before you have the problem. If you wait until everything's all loaded in and set up and you're in the middle of tech, at that point it's hard to move things around because you've had to negotiate all those positions with everybody, and it's hard to move things at that point. But if you can move them before, like when you're having that meeting about who gets to put things where, if you know where things need to be in order to get your gain before feedback, that's your time. That's your time to get it where you want it to be. And you got to dig in your heels about that and really get it at the right place. Because once you get into the tech and it's happening, it's hard. Because if you have to move some things that you would, like if you have to move loudspeakers around, that's hard to do after tech started, because like most of the other places you would want to put it, there's probably other stuff there. There's probably scenery there and lighting there and, curtains there and people there. And other stuff has to move in order for you to move, and that's hard to do. There's a ripple effect there that kind of is hard to accommodate. So if you can deal with that before you get to that point, that's great. Move stuff around. Get things in different places. Get the microphones in a different spot. Get the loudspeakers in a different spot. Get these relationships better. Get the microphones close to the actor, right? Get the loudspeakers farther away from those microphones. Do what you got to get the number you need, and do it then. If you don't figure this out before you have that meeting, then you're missing your chance to get this right, okay? So getting those distances and those relationships right, like at that point, is critical. And then after that, you get them where you can get them, and you get it as close to the optimal place as you can. And then at that point, you got to worry about using directivity to get you the rest of the way. Okay? You worry about, can I leverage microphone directivity? In some cases, yes. In some cases, no. Can I leverage loudspeaker directivity? In some cases, yes. Some cases, no. So far, when we've been talking about loudspeaker directivity, we've just been talking about, well, how even can you make the sound across the audience? And yeah, that's an important goal. But you want to be able to get it even across the audience without it getting on the stage, because the stage is where the microphones are. So you have to figure out how to get the sound to distribute evenly in the audience while not distributing very well onto the stage. Because if you're painting the stage with a bunch of sound, you're not going to have a lot of gain for feedback. Okay, so that now becomes part of your equation. Using directivity to help with the feedback is about keeping the sound off the stage, because the stage is where the mics are. Okay? So just to drive things home a little bit, the question is, well, how much gain do you need, and what is that like? Well, here's a scenario where we have no gain before feedback. Okay, this is, if you're not paying attention and you're not figuring this out ahead of time, and you get all this stuff put in the wrong place, it's very easy for you to get in a situation like this where you have no gain before feedback. That sound system, somebody spent a lot of money on a sound system that is never going to get turned on, because all it's going to do is make things worse. Okay? Well, what is that going to be like for this person operating the show? Well, okay, we moved it a little bit. Now we got 1 dB of gain. Okay? Well, let's see. So here they go. They've got their fader. They're pushing the fader. They're pushing the fader. Nothing's happening yet. You got to get to a point where you're making a difference, right? So nothing's happening yet. No, nothing yet. Nothing yet. Nothing yet. Okay, something. And then just as you hit something, it starts. You go any one notch past. I'm doing something, and you have feedback. Okay. Anybody ever been in that situation? Nothing. 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 Oh, something. Crap. I've been in that situation. It's not fun. Not a fun place to be. Eric?
Yeah, I mean, I've sort of been in that situation working on Little Theater.
Yeah.
Like when I was working on this middle to high school version of Rock of Ages, we did have some problems with the mics about that. So
yeah.
One solution that we did do is we used like low pass frequency filters, which we thought was clipping
Yeah, so you will notice that I have not invoked the word EQ yet in this discussion. Most people will try to solve this problem by grabbing an equalizer. And that is the exact wrong tool to use. Okay? A lot of people spend a lot of money on graphic EQs to solve this problem. Because, and I understand why. Because, okay, there's a frequency that is feeding back. I need to stop that frequency from getting through my sound system. And so you can go find a slider on that graphic EQ that is close to that frequency, and you can notch that out, and now that frequency isn't allowed to go through your sound system. Problem solved, right? I guess, but you've now created a new problem. Because that graphic EQ is nowhere near as surgical as you imagine it to be. Okay, that one little slider actually takes out an octave and a half worth of frequencies. It's a third octave filter, and that's just a third octave between 6 dB down points. But there's way more sound that gets affected by that. So you take that one slider out, and you are affecting an octave and a half worth of frequencies in your spectrum. And you're going to spend a lot of time trying to tune this sound system, get it sounding really good, and then to get rid of a sine wave, you're going to take out an octave and a half to some extent. It's really not a very good strategy. And what ends up happening is you do that, and great, you've killed that sine wave, but guess what? You maybe push it another dB or two, and now a different frequency kicks in, right? Now a different frequency locks into a 0-degree phase relationship, and that one starts feeding it back. Oh, crap, now I got to grab another slider. Get rid of that. Pretty soon, you've done this 5 or 6 times. You've completely obliterated the frequency response of your sound system, and you've gotten yourself maybe 3 to 6 more dB of gain at best. And then, like, you're out of tricks. The only bit of EQ I will ever allow myself to do that can help with gain before feedback is a high-pass filter. And the reason there is that, generally speaking, for most of the things you're going to put a mic in front of, the low frequencies are not super important. The really low frequencies, right? Your voice, a human voice, even somebody with a really deep voice, there's not going to be a whole lot going on below 200 hertz. So there's not really a whole lot of point in trying to amplify 100 hertz on a microphone that's picking up a voice, right? So that's a range of frequencies that the only thing that's going to get amplified is not that person's voice. So it's going to be something else. And therefore, you should go ahead and just like filter that out. And that can help with your gain before feedback because the first frequencies that feed back tend to be the low frequencies. Anybody want to guess why? Why would the low frequencies be the ones that feed back first? They are typically the most powerful because we are less sensitive to them, yes. They're more omnidirectional as well. They're harder to control. And therefore even the directivity, did someone else say that over here? No, okay.
We just said the same thing.
Okay, so even the directional loudspeakers and the directional microphones aren't as good at controlling low frequencies because of that size relationship we talked about a couple weeks ago. So they tend to, those low frequencies tend to be the first to feed back. And so if you filter those out, then that can actually have a pretty useful impact. So I would use those high-pass filters as liberally as possible. Because it solves other problems too, besides just feedback. There's a lot of other problems that those high-pass filters can solve for you. So there's a reason why, even on the cheapest of mixing consoles, you usually have one of those on every channel. It's because they're very useful. They solve a lot of problems, so use them. Okay, well, so here's the, that's the situation. Well, let's see if we can, fix the situation here. Let's just get the talker closer to the mic. Now we have 22.8, 23 dB of gain before feedback. What's that look like to this person running the show? Well, now this is where they are. So it's nothing, 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 something, something more, something more, something more. They can take it all the way to unity and a little bit beyond before it feeds back. And now they go maybe 3 or 4 dB past unity, and that's when it feeds back. Well, that's a pretty good situation to be in. You've got some room to work there. You've got a whole range there where you're making a difference. You can. That's useful. You can work with that. Okay? This is where you want to be. You want to be in this situation. So if you can get this right, this will be your reality instead of the other one. Okay? All right, that's it. Questions? All right.
Graphic helped a lot.
Okay, good.
Visual representation was wonderful.
Where do you find it?
Was it just on the library website?
You used to be able to find it on the website for my book until Adobe killed Flash and a PHP update destroyed the WordPress theme on my website. And so I still have not figured out the solution to both of those problems. I think I could probably convert the Flash to HTML5 using Adobe Animate if I could like take a minute to figure that out. I might be able to do that, but I still have to fix the PHP problem. Anyway, so no, you can't get it. But I will give you, I'm happy to give you the Swift file. I mean, I'm running the offline Flash player here, which is allowing me to still do it. That still works, but the web browser version doesn't work. But you should now know enough to do the homework. Okay, we're going to talk about acoustics on Thursday, but that's not part of the homework, so you should be able to do the homework now. And the thing I want you to walk away with here is, first of all, like, stop blaming actors on your feedback problems. And second, stop using EQs to solve your feedback problem, because like that doesn't work. So remember those things, and then remember that it's about moving things. It's not about turning knobs. Move things around.
That's the thing.
Okay.
I feel like all you want to do is adjust the knob.
The knobs don't help you.
The knobs are not your friends.
We're not about feedback anyway. They don't help you with feedback. But you have to physically move things to get feedback better. Okay? All right, folks, we're done. Thank you.